So, good morning, everyone. My name is VEDANSH, roll number 25. For my teacher's assessment, I am presenting on the mathematical backbone of quantum computing, eigenvalues, eigenvectors, Hermitian matrices, and unitary matrices. Now before we look at the equations, I want to ask a question. How do we translate the physical world into code? In classical computing, it's easy. We use bits, zeros and ones, and Boolean logic. But in quantum computing, the rules of physics, specifically quantum mechanics, take over. To describe nature, we don't use Boolean logic, we use linear algebra. In this video, I'm going to guide you through the four mathematical pillars that make this possible. We will see how vectors represent reality, how matrices represent time, and how specific rules, Hermitian and unitary, keep the universe from breaking. Uh, let's deep dive into eigenvalues and eigenvectors. So, normally, if I have a vector, let's call it V, and I multiply it by a matrix A, that vector will change. Here it is question mark, it's not displaying, but actually it's lambda. Lambda is eigenvalue, which is scale factor. So, that vector will change. Usually it gets knocked off course, it rotates and changes direction. But there are special stubborn vectors that refuse to rotate. When the matrix hits them, they stay pointing in the exact same direction. They only get stretched or shrunk. These are the eigenvectors. Okay. The amount they stretch or shrink is just a number. That number is eigenvalue denoted by lambda. This is lambda. Okay. So okay. Now mathematically this is just AV is equal to lambda V. But why does a physicist or a computer scientist care? This equation is actually the definition of measurement. In the quantum world, a system can be in a superposition, a mix of many states at once. But when we measure it, we never see a mix, we only see one definite result. The matrix is the question we ask the system. The eigenvector is the state the system collapses into. And the eigenvalue, that is the answer we get. For example, if I measure the spin of an electron, I might get plus 1 or minus 1. Those numbers, plus 1 and minus 1, are the eigenvalues. The state of spin up or spin down are the eigenvectors. Okay, so Hermitian matrices. This leads us directly to our next topic. If the eigenvalue represents the result of a measurement, there is a strict rule it must follow. It must be a real number. We cannot measure 2i meters of distance or 3i joules of energy. Our instruments only read real numbers. So we need a special type of matrix that guarantees its eigenvalues will always be real, no matter what. Okay, so this is where the Hermitian matrix comes in. Mathematically, a matrix such is Hermitian if it is equal to its own conjugate, transpose, S is equal to H cross. This means you flip the matrix across the diagonal and swap the signs of any imaginary numbers. Plus becomes minus. Because of this symmetry, the math guarantees that all eigenvalues are real. Therefore, in quantum computing, any physical quantity we want to measure, whether it's energy, position, or spin, is represented by a Hermitian matrix. We call this observables. Now, unitary matrices. So, Hermitian matrices are for measuring, but how do we compute? How do we change a qubit from 0 to 1 or create superposition? For that, we need unitary matrices. A matrix U is unitary if its conjugate transpose is essentially its inverse, U cross. U is equal to I. The most important property of a unitary matrix is that it preserves the norm or the length of the vector. Shutterstock, explore. Think about it this way. The length of a quantum state vector represents the total probability of the system. The probability of the qubit being 0 plus the probability of it being 1 must add up to 100% or 1. If a quantum gate stretch the vector, the probability might become 120% or 50%, which is impossible. So, quantum gates cannot stretch the vector. They can only rotate it around the sphere. This is why every logic in a quantum computer, the Hadamard gate, the CNOT gate, the Poly-X gate, is a unitary matrix. They process information without leaking probability. Okay. So, the connection or the comparison. So, to summarize the difference, because this is the most critical part of the assessment, unitary matrix are the operators. They are like the gears in the machine. They move in the state forward in time, they perform logic, and they preserve probability. Hermitian matrices are the observers. They stop the computation to check the result. They collapse the state and give us a real number. A quantum algorithm is simply a sandwich. We prepare a state, apply unitary matrices to change it, and apply a Hermitian matrix to read it. Okay, so in conclusion, quantum computing often sounds like magic, but under the hood, it is strictly rigorous linear algebra. By mastering eigen values, we understand measurement. By using Hermitian matrices, we ensure our results are real. And by using unitary matrices, we ensure our computation is stable. I hope this presentation helped clarify the mathematical structure of this subject. Uh, Thank you for listening.